Okay. Hi everyone, my topic is thermal stress and failure location analysis for silicon vide in 3D integration, and my name is Hou Bai Hong. So, today my video will go into 6 parts. First is background, and second is core research question, and third is simulation framework and assumption. Fourth is simulation result and analysis. Fourth is expected impact and application. And the final is conclusion. So first, the background. As the device scaling approaches its physical limit, the semiconductor industry has shifted its focus toward advanced packaging and 3D IC technologies. 3D IC used through silicon vide, or called as TSV, to achieve vertical connection, enable higher packaging density, better heterogeneous integration, and improve performance. However, TSV involves multi-material includes silicon oxide, copper, and nickel, and those metals have very different coefficients of thermal expansion. So, this work focuses on answering the following key question. What does the actual thermal stress distribution like? And what does the maximum stress occur at the different metal edge or interface or a bonding pad corner? However, do TSV geometry pyramids such as how do TSV geometry pyramids such as diameter ratio, pitch, and pad size affect the thermal stress? And in the multi-layer TSV bonding structure, what new failure path may appear? Then, the simulation framework and assumption. The picture and the structure as shown in the figure. And here is a side view. And we can see this researcher developed a 3D axis symmetry finite element model of a 2x2 annular TSV array. And these major assumptions are all measurable properties are isotropic and temperature independent, and the stress-free reference temperature is set to 25 degrees, and the interface are assumed to remain perfectly bonding void, and cracks are ignored. Plastic models are applied to a copper and nickel to simulate their plastic deformation during the thermal cycling. Instead, we can accurately observe how stress develops during the heating and the cooling. So, the result and analysis is when the temperature rising from room temperature to 125 degrees, and the drop from the room temperature to a negative 45 degrees, the maximum stress on the structure will occur on the nickel-silicon surface interface and in the silicon region of the bonding pad, respectively. Both scenarios may ultimately lead to the nickel fraction from the annular edge of the structure. We can see that the edge is red here. This is a temperature rising, and when temperature cooling, we can see the corner is red, so there is stressful. Okay, so for the structural parameters, diameter ratio, pad size, and pitch, we can get less when the size and the diameter increase, ratio and diameter increase, the stress also increase, and the pitch increase, the stress will decrease. Okay, so there is impact and application. So this outcome can application in the identify the high risk design earlier and provide TSV dimension and material selection guideline and reveal failure location and their physical mechanic. And here is the conclusion. To summarize, this research analysis identify and clarify how the geometry or the physics doing